Officially start. Hello, everyone. Welcome to the next meetup organized jointly by quantum computing groups from Washington, D.C., Warsaw, and Toronto. My name is Pavel. I will be the moderator today, and we have pleasure to host our great speaker, Eric Reiter, for the third time already, and he will give a talk about a serious challenge to quantum mechanics. This is part 3. This time will be focused more on the theory. So as you can see, this lecture will be recorded. So hopefully the video will be available later on our YouTube channel. And we've agreed with Eric that if you have any questions, please post your questions on the chat and or keep your questions for the end. There will be a dedicated Q&A session at the end. So we'll have time to ask your questions and you can get the answers. Before we start, would like to announce our next meetups. So the next one will be in December. Dr. Vlatko Vedral will give a talk about the twisted quantum logic. Sebastian will be the moderator. Then 1 week later, there will be a talk about quantum computing for quantum chemistry. And in January, Noaila Inan will give a talk about quantum machine learning and computing for financial fraud detection and market prediction. And finally, in February, Dr. Jarek Duda will give a talk about the two-way quantum computing by adding post-preparation as reversed state preparation process to attack NP problems. And finally, we would like to thank our partners and sponsors for supporting us, helping us organize these meetups. And yeah, I think we are ready to start. So I'm now stopping sharing my slides. And yes, we can see.
I'm on. So I thanks to Helen Ma for sure. Excuse me. The lecture slides are way too complicated, and it's best to just follow the mouse. And the lecture slides are also for reading later. There's all these details, and it's full of links. And so what my work is about, I'm going to give a very brief view of what the theory is that quantization will immediately lead to non-locality.
Screen. You've got a full screen.
Yes, could you maybe turn the full screen option? Yes.
How's that?
It's
better?
Almost.
Better,
It's better. It's better. Okay, I think we can continue.
Good. I like that. Right. Other people will interpret quantum mechanics, find interpretations, or devise wave properties of particles. My method is different. My method is about replacing what looks like quantization with wave properties to explain the particle-like effects. I end up with a two-state solution, wave state and a particle state, which is very different from complementarity. So I'm saying if you see wave effects, it really is about a wave state and not about particles going across space. So I do this with properties of the matter wave, which are thresholds, beats, and ratios that are ideas related to past experiments. And I'll show you that. I apply these properties to our famous constants of charge, action, and mass, and to our most fundamental equations. And so the theory predicts experiments that says everything is thresholded, not quantized, and I call it the threshold model. So I want everybody to fully understand what I'm talking about. So I do this little skit with cups to say what the threshold model is about. And so I'll start with a full cup, and I'll pour it over here to two other partially full cups. So I'm saying it's a rule. You only see when the whole cup spills over. You only see when all of it spills over. You don't see a partially loaded state. So you start with one that's full, you pour it over here, and then you have two that are full, and then the two will spill over. So I'm saying this is a way to see a 2-for-1 effect that I predict from the theory and show experimentally. Okay. So so we're going to go way back and realize that people have used the particle model for atoms and the model of the electron. And what I want to point out is that there were two very different states of matter when the great J.J. Thomson did the charge to mass experiment. It was in free space. But then Townsend and J.J. did the liquid drop balancing method, which is in a bulk matter system. And with that, you can extract the charge constant. So we're going to get back to how these constants are handled later. But I'm saying that our threshold model can explain these experiments and many experiments with wave properties, where you do not need the particle model to in both of these experiments. Even though it shows itself quantized, there's a sub-quanta state that I'm identifying, like I tried to show with the cups. So going back, 1900, Planck's great theory to for the experiment, for the equation of the experiment of black body. People say that he quantized light. Well, it's not true. You go back to Planck's work, and also he clarified it in other books pretty straight away, that his constant was a property of matter. It's vibrational energy, not electromagnetic energy in space. Now, there are many derivations that could do it with quantized energy. It could be done both ways. My point is what he did, and it can be done where you do not need to quantize energy for the black body equation. So then, of course, Einstein came up with the particle of light method for the photoelectric effect, and many people argued against it, but it was soon embraced. The great Lorentz argued against it, paraphrasing, light quanta just won't do. He did this nice paper with a telescope, how the light spread out. It was very convincing. And all these other great people argued against the photon model. So this is from Bohr's book about the discussions with Einstein. And this is a beautiful sentence that puts together the model of quantum mechanics all in one sentence, and both theoretically and experimentally. So it's important that I just read it. Well, first, it's impossible to visualize what's going on. It's about a contradiction. If a semi-reflecting mirror is placed in the way of a photon, now a photon at this point is assumed to be h nu of energy, leaving two possibilities for its direction of propagation. The photon may either be recorded on one and only one of two photographic plates situated at great distances in the two directions in question, or else, and this is part two of the model, by replacing the plates by mirrors, observe effects exhibiting an interference between the two reflected wave trains. So right away, it's a contradiction, and it's much better to understand that the photon word is about a model, not a thing, as very clearly explained what the model is. And we know this from how people have done the experiment that this sentence describes, even both parts of the sentence. Oh, and here it is graphically, one way or another at a beam splitter. And it's thought that it would go this way if energy is quantized. So the model of quantum mechanics comes from way back, energy being quantized. Of course, this is the other half of the photon model. Photon model is about both halves, both parts. And of course, you'll see an interference pattern that develops over time. So, so this is the experimental depiction of that sentence. We're going to show that it's this first part of the photon model to fail. I'll demonstrate this, and we're going to show the history of people doing this experiment. So this first part of the photon model and all of it was written up very nicely here about in Heisenberg's book, where right away you can tell the photon model implies wave particle duality and superposition and quantum. Let me go back. To go one way and not the other way is a one particle entanglement. You don't need two particles to understand entanglement. You could understand it right here. And he explains it pretty well about how they think of it as all connected that way. So right away, you end up with all of these acts of desperation. And that's where we are now. It has not changed ever since these early writings as to what the model of quantum mechanics is and what it implies. So it's very good that Planck had literature. I did a translation. You'll find it on my website. It's in German. I translated it to English. It's a loading theory where light energy could be absorbed and accumulate, and then there could be a sudden release. And so we only see these, what looks like quantized releases of energy in his theory. If you look at the algebra, and I make it nice for you, his constant is expressing a maximum. It does not have to be a threshold of action. It could be a maximum of action in his second theory. Also, again, Planck's constant is a property of matter, not light. There was an important average of the energy that came out of his theory, which is like h over 2, a half an action, or h nu over 2. And that's an important 0-point energy term that is consistent with everything else I do. It's also used in low temperature physics. So Millikan agonized over the photoelectric effect, and he argued for an alternative that he called the loading theory. And so he did not like the photon model. He understood there were all these problems with it. So there's this idea where the energy would load up and only need a minute addition to then release all of it to show this threshold effect. But he didn't understand how it could work, and he gave up. So after this, in his book, 1935, I looked all over. I couldn't see anybody who worked on this idea. This seems to be the last mention of this idea of a minute addition in all of our literature. But I take it as that's the way to go. So I'm going to review. This is the models of absorption and emissions. This is Planck's quantized absorption and emission. His second theory of continuous absorption, but it was continuous and constant, you see. Now, the idea of Millikan is that there could be some place where it doesn't have to be a constant continuous. It could be arbitrary way to get up to the threshold. And then by some tickle, it would just all be emitting. And so this idea is what I perfect. And so what happened was when people compared to experiment. This second theory is what they were using, but it didn't work. I'll show you that. And the Millikan's idea was just gone to obscurity. So here's where people handle the loading theory. Here's why the loading theory was forgotten. It's in important books where they compare how long would it take to load up in an experiment and compared to a calculation. And it takes way too long if you calculate by that continuous absorption. And so they're giving this as a homework problem to teach everybody away from the loading theory. And so they're not including the idea that there could be any kind of preloaded state which could make it work. But they don't do that. They teach away from that. Then the Compton effect came up both theoretically and experimentally. And the theory treats as if it's quantized energy in the derivation to explain the effect. And what happened was people started thinking of energy conservation of quantization. And you could see in their writing and in plenty of other places that they talk about energy conservation as needing quantization, but it's just not true. That's the model of quantization that they're applying, I say, prematurely. And similar things happened here when they're testing the Compton effect, element of time in the Compton effect, where they don't understand how they're also explain these responses of both the electron and electromagnetic signatures in their experiments. What happened here? So now we're going to get to de Broglie's theory. So he says E equals h nu. That's pretty cool. We're going to use that. E equals mc squared. Oh yeah, we know that. Let's just cram them together. Well, this equation will work for pair creation and annihilation. If you put a delta in front of the mc squared, and you have to put that delta, then you'll get energy of a gamma ray and the loss of mass in the atom that emitted the gamma ray. That makes sense. That worked. But if you were to use this equation to calculate the frequency of an electron, and then look at the de Broglie equation, where you can easily calculate the frequency of the electron from the wavelength and the velocity, you get completely different answers, and this is variable with velocity. And these two just don't connect together. They don't make sense to even use this as a derivation, but they do. And so that's problem number one. Problem number two is the c squared equation equals the phase velocity times the group velocity. And of course, if the group velocity goes less than the speed of light, the phase velocity would be faster than the speed of light. The group velocity is usually taken as the particle velocity. And quantum people just love this because it's justification for the ghost wave, that there's just something going faster than the speed of light that's behind everything. But I'm saying, no, we could derive the wavelength equation in a completely different way without these problems. And well, it was accepted because the experiments soon after showed that the wavelength equation was true. It worked. So when people see that the equation worked by experiment, people think there's something right about the derivation. But again, there are many ways to derive an experiment that fits an equation where the model can be different. And so that's the name of the game in physics, to find consistent models over all these experiments. G.P. Thomson was J.J. Thomson's son, and Davis and Germer, they did charge diffraction. Schrodinger used the de Broglie equation, but I was taught and looked that he didn't use this derivation. He just used the equation, and that's okay. It was right. He used it before it was experimentally substantiated. So Schrodinger, of course, he's famous for his equation, but there's something else really beautiful in the same paper of Schrodinger that I'm pointing out, where he talks about the envelope, the deep difference tones, the beats of charge are related to how light interacts with charge. The envelope of his psi is the electron, and light interacts with the electron this way. So we're going to pull out Bohr's hydrogen spectrum equation, and it's usually written where h nu equals constants of a difference in two terms. So with this, well, first we're going to take the h and put it on the other side, get a h cubed in the denominator. The frequency of the beats is equal to a difference frequency of the inner waves. This is a big clue. The hydrogen spectrum are telling us about beats, as inspired by Schrodinger. I make a factor of 2 correction as to just how he said that. We'll see that. Oh, also, there's this h cubed that we're going to see again. We're going to use that h cubed construct. That's a big clue. Schrodinger hated quantum mechanics very plainly. So here's the h cubed. Excuse me. Bose did a derivation of the black body equation with standing waves of light. And I looked at this derivation and just did a simple transposing and using the standing waves of psi, his inner wave, to generate the black body spectrum equation. So this is important clue as to what's going on with Planck's constant and the nature of these beats. So this is something you'd have to click and see. In my other writings, I have much more theory that I'm not going to be able to explain here. It's way too tedious. I'm just pointing out that I did it. Similarly with, well, what is antimatter? There's a way of seeing how the inner wave can cancel to show why is it and how that electron and positron will cancel out and leave the envelope, which is how light interacts. This envelope is about light, and that will collapse and emit the 2 gamma rays. And similarly, like how do you picture Planck's constant where frequency will make it change the shape, but the area of the beat is conserved? That's what Planck's constant is about. It's about these beats that have a conserved area, but the area is a maximum when it's stable in the atom, but it can load up. The beat can build up. So that's my theory. There's a lot more. I identify, well, how is spin pictured as a counter-rotating psi wave of 2 slightly different frequencies, and the whole, it's like a jump rope where waves go in opposite directions, and it'll spin around at the splitting of the spectral line frequency. And so that's a way of picturing spin. So I did all these pictorial representations, and you can read about it in my other paper. But so I'm going to take this beat idea and now derive the wavelength equation with it. Well, I'm going to start with the photoelectric effect equation. The message of the photoelectric effect is really a combination of these two constants. So we're going to, what's usually done is that they borrow from a different experiment the charge constant, and then you get to see that maybe the photoelectric effect is another way of seeing Planck's constant, but really the photoelectric effect experiment and equation is about this conserved ratio, the H to E ratio. But we respect our constants, and we're going to pull out the conversion between voltage and kinetic energy and write the photoelectric effect equation in terms of kinetic energy. Then we're going to see, well, what's the velocity? We're going to call it the velocity of the beat. The G is about a group. And we're going to use this fact to see that there are two fit the light wave. And it's not just one beat, because then you'd have to square it. And I make this discussion about that it's linear, and that's consistent with the linear photoelectric equation. So we use velocity equals frequency times wavelength, and we get something that looks like the de Broglie equation, okay? But, however, what is this mass term? That looks like a particle, and it's in the same equation as a wave. So here's wave particle. We're going to fix that. We fix it by using the same trick that Planck did, by saying charge is thresholded and mass is thresholded. We're going to see how that makes some sense. So when you do that, then I write this non-dualistic wavelength equation. And this will work for atoms like, can you diffract buckyballs with this? And I say no. There's some calculations I did on the papers who diffracted giant molecules, and I show it's in my previous lecture where I go to the details of other people's experiments who will try to argue that quantum mechanics is right because they did things like diffracting buckyballs. Well, it's their experiment and interpretation is full of problems. You have to use van der Waals forces, which is a particle thing against the slits, and the shape of the spectrum doesn't fit by wave theory. Excuse me. It's hard to imagine that such a thing as a buckyball will load up. And that's what I'm saying is happening at the absorption. So we're going to, so this is the key. We're going to look at equations for the experiments that are famous for the wave properties and realize that there are these ratios. The electron diffraction experiment, for instance, it has a H to M ratio. What does the experiment tell us? Without borrowing a constant from someplace else, the message of the experiment is a conserved ratio, this Q. So that's the trick, that there's such a thing as a conserved ratio. It's the ratios that are quantized, and that the constants are thresholds. Similarly, here's the Arnav-Bohm charge diffraction experiment. It has an E to H ratio. What's the message of the experiment? The ratio, and on and on. So it's a beautiful symmetry that I discovered about the equations that display wave effect have these conserved ratios. So then it gets to the argument, well, the Millikan oil drop test, that just says charge is quantized. And I'm doing this radical thing. I'm saying charge is thresholded. How do I get off doing that? Well, you'll see. It looks like what's happening is that it's the threshold that gets expressed in bulk matter experiments. There's a nuclear wave function that makes an ensemble effect over all of this because it's two different states of matter. There's the beaming in space experiments, and then there's the bulk matter experiments. And it's a big assumption to say that it's quantized for the beam experiments because they're diffracting. How can particles diffract? I'm saying it's not a particle if it diffracts. And what gets transmitted across space is the ratio that's conserved. And then it transmits its identity that way. And that's how when a detector goes click, it doesn't have to be a particle that lands there because what went across space has shown diffraction effects. The type of wave is encoded in the ratio that's conserved in any piece of the wave. I'm just drawing a volume here of the wave with a conserved ratio. This is the resolution of wave particle duality. So that's theoretically the justification. What about experiments? It calls for evidence of subquantized charge, subquantized energy, and subquantized mass, or any one or all. I don't know. I show all of it. So to test if energy is quantized, everybody does this beam split coincidence experiment. The particle part of the photon model that I showed earlier. So, and they compare to chance. They invoke the photon model and compare the clicks to see if it goes both ways together more often than accidental chance or less than chance. If it goes less than chance, it's like it gets pushed one way or the other. And that's the model of the photon. So looking inside as to what goes on, what I'm getting to is that it's like the cups I was showing earlier, where there could be partially loaded states. A h nu emitted will fill something here, like an electron. It'll all give up the whole amount of kinetic energy. In the case of light and electrons, it's kinetic energy that loads up. Here, similarly, there's partially loaded states, and it could give up a detection click 2. I'm looking for a 2-for-1 effect to be able to be seen energetically. We need energy resolution, we need time resolution, and we need assurance of single emission to show this is true. Now, no one has employed energy resolution in any of these tests. I'm the one to do it because there is no pulse height resolution from light detectors, any light detector. They have a wide distribution of pulse heights. But gamma rays do not have this problem. You have on the horizontal is pulse height is proportional to frequency, electromagnetic frequency, and the h nu energy of detection. E equals h nu is still true, but it's only in the clicks. The energy of emission suddenly and the energy of absorption that reaches a threshold suddenly is E equals h nu. So we're able to look at just these pulses that tell us the energy in our experiment. We have energy resolution. Also, when you use gamma rays, we have a much better way to determine whether the source is one at a time. I'll get to that. So we're going to review the experiments that were done in the past. First one, 1946. They did the theory right. They're comparing to chance in the right experiment, the beam split experiment. They see the rate of experimental coincidences compared to the chance rate is equal to about 1, and that's consistent with what quantum mechanics would predict. But of course, it had all these problems because they had no pulse height resolution in these detectors. Similarly, with visible light, here's a beam split. They used the chance equation right. And they do this really great, which is a time difference histogram. What time is it between the two clicks? So when they insert a large pulse, you will get coincidences that make a big peak in this histogram. So this is their when they dim the light, it's a band of noise. So it looks like quantum mechanics, but of course it has these problems. But still, they understand in this Nature paper that if you get a peak, if you see some correlation, you're going to have to rewrite quantum mechanics. This is really important stuff. Next test, it's kind of complicated with the work of Clauser because there are two beam split experiments. It's like the same timing histogram, and they see the band of noise, that there's not coincidences. That's consistent with quantum mechanics. These other peaks are control tests. So, and there are other problems, like he used polarized beam splitters, which can route the light and so on. Then there's the Aspey's team in France, where it's a triple coincidence test. Of course, it's emitting two H nus. They try to catch with big lenses what happens to go in opposite directions. And they use over here as a trigger. And the problem is they do not use the triple coincidence chance equation. They derive something else, which I argue against doing that. Anyway, what's good about this paper is that they at least try to show both parts of the model of the photon, the particle part and the wave part. They mislabel it here. They talk about a photon. It's not a photon entering the Mach-Zehnder because they didn't put in the wire that goes around, and they explain this in their text, that it's a triple coincidence back here as to what's going on. It's called heralded, and I argue against doing that. But they don't use the triple coincidence chance equation. We're going to get into that soon. So now they're teaching how to do this. At this year, they've developed this parametric down conversion thing where I can argue against that, and other people have. And it's obviously a triple coincidence equation experiment. They don't use the triple coincidence equation. I don't know how they get this rate, which should be a time window, like here. There's a time window. They don't use a time window in their comparison to chance. This is the rate of the triple coincidence, and this is somehow about chance. I don't see the time window how that could fit in there. Maybe it does. It doesn't matter. They went and took this equation and said, oh, it's not good enough. And they made up another equation. And they say this comparison to chance, this is their chance equation. And then when they compare the experimental triple coincidence using this, they get less than chance. And that's what they put in their table of data. What's good about this paper is they give numbers so you can see what they did. And so I do a few calculations on it, and it just doesn't make sense, really, what they're talking about. This is the triple coincidence chance equation that they should use. The nuclear physicists use this regularly. It's well tried and true. Everyone knows about it. They do not use it. They do not see photons. And I'm saying the whole mess of them have done this experiment wrong, to where they don't know how to look for a reasonable alternative to photons. They're making these mistakes in their experimental setup, and they're making mistakes in the equation that they use to compare to chance. Straight away, I do it with gamma rays, and I avoid all those problems. And this is what's really important. The one at a time emission test that the nuclear physicists use, they all love it. That's how we see all the energy levels of the whole periodic table. You put the radioisotope in between a pair of detectors, and you use the time difference histogram to see if there's a peak, or you just compare to chance by doing the singles counts. And so there's no peak. And so the radioisotope I use, they publish that it just emits one at a time. And I test it also the same way. And I see this. That was in my previous lecture where I showed that, the details of it. So there's no question about whether we emit one at a time. And so now I'm going to have the gamma ray collimated towards a pair of detectors. In this design, I have a thin in front of a thick detector, like I showed earlier with the cups. And I've done it every way where it looks like a beam splitter and all different geometries. But this way works pretty much the best. So this is the time difference histogram. And we're going to look at this time range. This is the time window that other people use as well. And we put that into the chance equation along with the singles rates, where we're counting the full height pulses in the singles rates. That's not coincidence here. We're counting that. This is how everybody does the chance calculation. I showed you everybody does that. And so we'll do the ratio of the experimental rate to chance, and we get 6 times chance. Quantum mechanics fails. That's it. It's over. So we have all these advantages. We have energy resolution. We have a clear way of seeing that it's a one at a time. I've done it many different ways with different detectors and so on. Why was this effect not previously noticed? Well, good reasons, a whole list. This is a graph of the absorption in our sodium iodide detector versus the electron volts of detection, also the frequency and pulse height on the horizontal. There are various mechanisms of absorption in the detector that is in many nuclear physics books, and I agree with them. There's a photoelectric effect mechanism, and there's a Compton effect mechanism. Now, I discovered that the photoelectric effect needs to dominate over the Compton effect in the detector for the gamma ray that we use to see the sub-quantum effect, to see it defy the chance ratio, the ratio above chance. Now, there are only two isotopes to use here that work any good. If you're over here, you'll hardly see the effect. And also, if you use the wrong detector, if you use the high purity germanium detector, which is the best for energy resolution, this situation becomes worse. The Compton effect rises up in the other detector. So it's best to use sodium iodide, which has this property. And then what do we have available to us? There's only the gamma ray needs to only emit one per radioactive decay. Many of them emit two, and you see that in the sandwich test. And there are these two that emit one at a time. It has to decay to a stable state. It can't just decay and then emit again, whatever it decays to. It has to have a reasonable half-life. Nature was kind to me to let me have these two radioisotopes to work with. Otherwise, I wouldn't see it. I started out up here, and I did not see the effect, and I kept studying and working on it to figure this out. Also, who would expect that the most particle-like kind of light would show that light is not particles? Well, that's what happened. I did these experiments as far back as 2001, and the theory as far back as year 2000. I've been working on this pretty much the whole time. This is a triple coincidence test with gamma rays, and this nails it down pretty well. Sodium-22 will emit a positron that finds an electron, and they annihilate a pair of gamma rays. It also emits in the same decay a hotter gamma that I use as a trigger. So I'm able to do a triple coincidence. So these are different detectors. I think they're bismuth germanate that have the photoelectric efficiency better to show what I was doing before. Sodium iodide will not work here. So I built these detectors, and the pulse heights are for the 511 keV annihilation gamma. And so right away, even if it's just a pair of detectors, it makes this gigantic peak, and it's the subquantum effect showing. Putting in the third detector, we get a very visible peak that we could put into the numbers with a chance equation. This is the triple coincidence chance equation. And when you compare to the rate in this section of which we count as the time window here. So the time window is used in two places. It's used in the range of which we count over to say how many are in coincidence. And it's also used in the chance equation. You do that comparison, and that's how the first two papers, at least, were done just the same way. We get 500 times chance. The details of this are further, you can click on. And this experiment eliminates the possibility of stimulated emission. And there were other experiments that I did. Someone might say, well, maybe I discovered stimulated emission. And there's all kinds of things that people will come up with and say, oh, well, maybe it's this or that. I've been looking at this for all these years, and I've done many experiments, tests, like maybe it's lead fluorescence or something. So I've eliminated these artifacts with both experiment and theory. And we'll see, maybe someone will throw something else at me. Now we're going to return to the Compton effect. The equation for the effect can be done with waves. It's in Compton's book where he did a wave derivation. This is a beautiful symmetry of showing that a wave derivation and a particle derivation can come up with the same thing. Now, there were some clumsiness about how they did it. Compton was inspired by an earlier paper by Schrödinger. That's great. They had two de Broglie waves going against each other to form a envelope. Very kind of clumsy, and so nobody kept using this. So I'm repairing the model by using the beats in this new wavelength equation to start with. And then it's straightforward. You use Bragg diffraction equation, the Doppler effect, the Doppler shift equation, and a trigonometric identity. Out beautiful about this is that the wave model predicts that there could be a non-deflected wave that goes straight through. That idea is denied in the particle model. It's supposed to be energy conservation that goes particle this way and this way and this way. There is no straight through wave when they read these signatures in coincidence. So saith them. But I say, so it's cobalt 57, and this is a logarithmic graph. So this, of course, is way up there. This is the photo peak. This is the Compton effect, downshifted. Horizontal is pulse height here. It's a pulse height spectrum. Vertical is how many. So you can add, what happens is inside the scintillator crystal, it makes flashes of light. If they happen superimposed in time, it makes a bigger flash of light. And everybody knows that. They talk about it. But they don't analyze with this detector at this radioisotope and to look at this part of the spectrum, which is what you need to do. And so there's this anomalous shelf of pulses at the position that's twice as big. If you add these two, these two would be the 122 keV plus the downshifted will be over here. So what makes this is a signature of the straight through undeflected Compton effect at this section here. This is two of the full height pulses. Actually, the two full brightness flashes of light that make a twice high pulse in the detector, which is here. And so here again, this is the other isotope, and you get to clearly see the signature of the Compton addition plus the photopeak addition. And then this is the two photos adding up. And there's some analysis I did on the computer. So, and also here's all the numbers. Almost 6 times chance for what happens here. It's the subquantum effect. Quantum mechanics denies any of this to show up, except down here in the noise. So I kept going on this. What makes it tick? All different ways to do this experiment. It's an invention of a useful spectroscopy. So I put silicon wafers here at 2 different angles to see my coincidence effect, and saw that it lit up many times greater at when I rotated it about 60 degrees. And this is all written up in my patent application, which was very rudely rejected. Like they didn't get past the title on it, because what is it? Photon violation spectroscopy? Trash. It all worked. Everything here worked. it all made sense, the different ways that I looked at this. What happens if you put a magnetic field on the scatterer for ferromagnetics and diamagnetic substances? Well, you get to see whether the bond is flexible or stiff. Beautiful things you get to see about the bonds. I went and electroplated the radioisotope to make a metallic chemical state and compared it to the crystalline state of the radioisotope source to see if it made a difference. And it did. It made an incredible difference. It's a discovery as to how chemistry and affects nuclear mechanism. It's been a long sought other people searching for it and doing it. They barely see it. This is robust to see the effect in the subquantum effect. Here I'm cooling the beam splitter, which is a slab of aluminum in front of two detectors, one detector and then to the other. And what did it do? It doubled the subquantum effect when it was cold. So everything worked in a direction that was reasonable for it to do under these splits in two. You can see if it, you can expect me. This is a triggered pulse height spectrum where we're looking at the pulse height spectrum that is triggered by another detector. This is a single detection in coincidence with, now here's two. If it makes two in the detector number one, it'll make a twice high pulse. Here it is. So this is 3 for 1. 1, 2, 3. This is a hint of 4 for 1. So it keeps going. Similarly, with the liquid nitrogen cooled high purity germanium detector inside of my giant shield, I built this incredible shield to do these experiments in. The shield cut down the background radiation to about a 30th of what would be otherwise. But the effect works without the shield. But I went through for many of these tests to do it in the shield. This is a spectrum without coincidence. You do not see this ×2 peak. I call it a ×2, where there's two flashes that superimpose. You don't see it. But in coincidence, it brings it out, where it's a 3 for 1 effect. 2 in this big detector, 1 in this detector, the trigger detector, in coincidence. And of course, it had this beautiful 1 bin peak for the photo peak. 7 times chance. Then using this idea of there could be multiple pulses from a single emitted h-nu, we're going to try to really figure out what's going on here with a gamma ray. If it's a classical ray, well, I realized ahead of time that we're looking at a near field shock wave of classical electromagnetic gamma ray. Such a classical ray would have like needle radiation with a transverse spread. We see it. So I do different distances to see, well, here the cone of gamma is too wide. Here it's too narrow. And here it's just right, compared to the sodium iodide absorber molecule. So we see it pretty plainly. Also, from looking at this, you can just see the way we're above chance by the ratio of the peak height. The peak height here is normalized, but what's important is the band of noise underneath is about this ratio of the peak to chance. So you could see how we differ with our ratio above chance just by looking at the graph. And it's not in this experiment that we get closer, that makes it work better, because this was closer and it worked worse. So there's a distance resonance that I discovered. So all these things about gamma rays and the matter wave and the matter wave. What about rest mass? To resolve wave-particle duality is about both. Atom diffraction, what's going on with that? That was really the hard part, to get a model that was consistent and understood with electron and atom diffraction. This was a beautiful experiment done by others where they focused helium. Well, can you focus particles? They try to do that with the probability wave or some pilot wave kind of thing. But that I call an act of desperation. Anyway, there's also the signature of the particle holding itself together, but there's both. Whatever's going across space has two states. It can hold itself together to make this signature, and it can focus to make that signature. Different emissions can be taking on either of that state. It's not like complementarity the way you look at it. Is that it's a soliton. Atoms are solitons. It could hold itself together or lose that ability to hold itself together and then spread. So to really tie it up, I do the beam split coincidence experiment with the matter wave, with the helium nuclear wave function, otherwise known as, they call it the alpha particle. Well, if it was a particle, it's going to go one way or another at a beam splitter. This is a thin foil of gold, kind of similar to what Rutherford did with alpha hitting gold foils, except now we're looking at the timing between two alpha detectors. So I went through great pains to automate the experiment so we can see the relationship of pulse height in this detector and pulse height in the other detector. And it's half height pulses for the most part. However, there are plenty of other experiments people have done where they try to split the alpha, and it takes 14 MeV of kinetic energy to split the alpha. We don't have that. We have 5.5 kinetic energy, 5.5 MeV of kinetic energy upon emission of the alpha ray from this radioisotope. So it's not like we're splitting into fragments like two deuterons. We're discovering something important here. What it looks like is that the charge to mass ratio is conserved and that we're slowing down the kinetic energy to make smaller pulses. And that's the way the detectors work. They're a function of kinetic energy as well as charge. But what's this? These are full height pulses. And you look at the numbers, how many, and you compare the singles rates and you compare the chance and all that. It's 4 times chance. And they're all perfectly behaved pulses. There was no background to subtract. Oh yeah, I subtract background in all these tests. You have to do that. The background coincidence rate is subtracted in all of these comparisons to chance. So this is a 2-for-1 effect, and it's a signature of 2 mass constants and 2 charge constants. So this substantiates my claim that about the charge being thresholded, and that it will load up here to make a 2-for-1 effect, that atoms are solitons, the wave can go across space, it transmits its identity by the conserved charge to mass ratio and action ratios in the matter wave. And that's what the matter waves are made of, how they transmit, how this all works. So we see it. Here's the evidence. And here's details of the experiment. There's more details you can see in my papers. You can click here. Oh, here's something interesting. There was Dr. Vidral, who's going to be talking in the next meeting of ours. A year ago, he talked about, well, somebody needs to do this experiment where you look at a coincidence of, he was describing this experiment where it's a matter wave that or splitting the particle in 2 ways. And so I piped up in this lecture a year ago, and I said, well, I did that experiment. And he said, oh, yeah, that's very nice. Anyway, you can see the clip of what happened a year ago, where he acknowledges that this is the experiment to do and that nobody did it. This here is the link to the whole lecture of his. Now, there is a better way that I tried very hard to see fractional charge in its more pure way. It's a mass spectrometer, and I was interacting with a electron gun to change the charge before it hit the magnet. And I was looking to see this dip change. Here's the signature that I was successfully able to see, the 3 charge states of the alpha ray. I wanted to see this dip go up, but I had trouble. I was not able to make the electron gun properly. So I'm posing this as a future experiment that I show just everybody how to do. I did this experiment, all these experiments, many ways. This is a partial list of all the ways that I've done this with different detectors and geometries and radioisotopes. This is to recap some of the things that I made note of before, but this part is important. I'm discovering a sub-quantized state, and if you look at the Bell theory, they do not talk about such a thing. All of Bell theory is about what shows up ahead of time at the detector. Their hidden variables are in the particle, not in the detector. And that clears up all of this Bell theorem comparison experiments and gets rid of all of these extreme views that people say, oh, it's not a debatable point anymore. Well, it's debatable now. Their experiments are flawed. The theory was flawed. They're both wrong. Bell's theory is wrong, and quantum mechanics are wrong. And the words matter. How we talk about this stuff. What I'm trying to say here is talk in terms of the clicks and the experiment, and not describe your experiment in terms of photons. It's not a thing, even by conventional quantum mechanics. In the way people describe, if you look at the papers, it's very misleading. Anyway, it's a big problem. If you have any doubt as to what I'm saying, this is an easy experiment to do. I tell you just how to get this isotope. You go to your school to do the spectrum, and you look at this shelf and do the calculation on it and try to explain it away. So that's my challenge to you. Argue with the experiment, then argue with me. I stand with Einstein, Schrodinger, and Lorentz, like I showed earlier. The preceding discussion should suffice to show that one cannot speak of light quantum that remains undivided and spatially concentrated. The photon model is just wrong. So here's my email address. I'm trying to make friends here. Please communicate with me, even if you think I'm wrong. Set up a conversation. Everything I've said is on this website. And it's about what I said, 50 minutes, 53 minutes. I'm ready to take questions.
Okay, great. Thanks, Eric. I can see that we have the first question on our chat. A question from George. Could neutrinos balance the books in the high energy gamma ray experiment?
I could not hear you.
Okay. Is it better now? Can you hear me?
Or I'm sorry. Go ahead again.
Yes, can you hear me now?
Yes.
Okay. The question from George. So he called it a crazy question. Could neutrinos balance the books in the high energy gamma ray experiment? Maybe George could unmute himself and
Could
clarify.
what balance the books in what high energy experiment?
Neutrinos.
Neutrinos.
Yes.
Oh,
In the high energy gamma ray experiment.
I'm not. Oh, huh. No. These detectors are not sensitive to neutrinos. There's neutrinos are few and far between. They would any other weirdons that you might dig up to say, well, maybe that's causing it, would show up in the experiment without the radioisotope. For one, you can eliminate the background, so you can subtract background. And if it was in the radioisotope, like if it's very difficult to detect neutrinos. The rate would be some few and far between, and so whatever I'm detecting would overwhelm it. So it's pretty easy to eliminate that idea. So I say pretty clearly, no, it's not neutrinos. So that's
Okay.
my take on that.
All right, good. Thanks. Yeah, so there is a comment from Dave. You would need a lot of neutrinos, probably hundreds of them. Good. Do we have more questions to Eric? Maybe someone would like to unmute.
Well, Dave here, I have a comment. I'm interested in the technology of the triple coincidence. Where where do you get the radioisotope that you're using?
It's sodium-22. I bought it from Atlantic Nuclear, and these buttons are like $150. And it's an amazing thing. They'll just sell you radioisotopes at license exempt quantities, like a few microcuries.
So you're getting a detection event every 10 or 100 seconds?
It depends how far away they are and the rates. You want to look at the rates of these things. The rates are in some of the numbers in my other experiments, like let's see here. I'm pointing to singles rates. These are like several hundred a second. This isn't for the sodium-22. This is for the other isotope in these detectors, but they're typically like in the hundreds of seconds.
Yeah.
Hundreds per second.
Right. And to get a triple coincidence, it's going to be, you know, some factor, maybe a factor of 1,000 above that.
Below. It's rare.
So if you're getting 100 a second, you're going to get a triple coincidence maybe every 10 seconds.
Uh, I'd have to look at the very numbers. I didn't
Okay.
put all the numbers in this slide. That's going to be in my paper to click for details.
Right.
So, but it's rare. You see, the triple coincidence equation is tau squared. So that makes it a low rate
Yeah.
for it all to be in coincidence.
Mhm.
And so one of the things I point out earlier is that the other people who do triple coincidence with light, they don't use this equation. They use a linear triple coincidence equation without tau squared. And they made it so the chance rate is much higher so that when they see that it's lower, it looks like it gets routed one way or the other, like a photon. So you have to maybe hear that a few times to get it straight. But it's all there in this slide as to what they did.
Okay.
And the same thing with these people. They did not use the triple coincidence chance equation. They made up this equation, and I don't really understand this. Maybe you can help me how they derived it, but it looks wrong from the get-go. And they shouldn't be using it at all. They should be using the triple coincidence chance equation.
Okay.
Okay.
And they have no energy resolution. Nobody's has some idea of, well, what would they look at to get a 2-for-1 effect? They're not thinking of it that way as to how to design something to see that, which would be the alternative to quantum mechanics.
All right. Thanks, Eric, for the answer, and thanks, Dave, for asking. Do we have more questions or maybe some comments?
I just got some question.
Yes.
Very generic, very general question. I, I just wonder what's the implication of this theory? You know, you do experiments, difficult to challenge your experiment because not many people do experiments. But I just think in terms of application, you know, currently there are lots of technologies that have been developed which are supposed to be based on quantum physics, quantum mechanics. Now,
Right.
if you're challenging these theories, so what does it mean for all this engineering technologies, quantum computers, quantum telecommunications, and et cetera, et cetera? So
Right.
it means they are wrong, or those engineers that develop these technologies,
Yeah.
or your theories are still valid for the engineering applications.
Yeah. Right. Right. So look, there's plenty that will be explained by quantum mechanics. But if you're looking for a macroscopic entanglement, that's what I'm saying is wrong. They're trying to see it, and they've been working and working, and they have trouble seeing it. And the literature on quantum computing and teleportation, whatever communication, when you look closely at it, to me, it reads like propaganda. I think they're all making a mistake. I'm not saying quantum mechanics fails in everything. It fails in the kinds of things that call for this long range entanglement. And then as far as applications, it's here. It's in these spectroscopies in material science that let you see what's going on. So there's plenty of things to use it for. Does that answer your question? I know it's hard to take. I know
Yeah.
it's hard to take because there's all these billions of dollars, big companies saying, oh, it has to work. It has to work. Well, it has to work because they think in terms of energy quantization. Is it really quantized? It's a stretch to say it's quantized. it implies the weirdness.
Yeah, but
Like
distance,
this.
when you talk about distance, about entanglement, there are claims from some organizations, and say, for instance, the Chinese last year or a few years ago, they claim to have managed to do communication,
I
from
know.
satellites to
Yeah,
ground,
yeah.
etc., use entanglement.
Yeah,
And
yeah.
you believe that this is wrong, or that distance is relatively short from
No.
the orbiter, satellite orbiter to ground.
I'm saying to look closely at the experiment to see what kind of assumptions they're making. What it looks like they're doing is looking at bands of noise that say it does not go one way or the other at a beam splitter. I'm saying they're looking at noise. They're misinterpreting their experiment. They're not designing an experiment to see through the alternative to quantum mechanics. So then they're interpreting it by entanglement.
So, but therefore, you accept that there will be it will be possible to make communication at a distance using.
No, no, I'm saying entanglement is just wrong. It doesn't work that way. They think it should work that way because of energy quantization and the interpretations of certain experiments.
Yeah. Okay.
But it's
Yeah,
not.
I understand. That's fine. Yeah. Thanks for your explanation.
Good. Mhm.
All right, thanks. There was a question from YouTube. So thanks, Helen. Do electrons exist as particles in your theory, even though their mass is the mean of a distribution?
There still are particles, of course. It's a two-state solution. It's like a soliton. We embrace particles in solid state. It's that when you start beaming across to do these wave experiments, it doesn't hold itself together as a particle anymore. How do you explain that? Is what I'm doing. The theory and the tests I do show that the particle probability model fails, where you beam across an alpha ray, it should only go one way or the other. Well, it doesn't. Nobody did that test except me to answer the question about the probability interpretation of the matter wave. So we still accept particles in a solid state. It pretty much holds itself together. It's about understanding these wave experiments and the flaw of quantum mechanics as to what's going on inside to see, is everything really formally quantized, or is quantum a part of the answer, the model? The threshold model is about, we usually see the thresholds, but there's a sub quantum state that's hidden, normally hidden, unless you look for it, the way I've done and showed you. And that resolves all this wave particle weirdness. So I'm saying to do the experiment is easy to do. You may be a theoretician. That's okay. Look at the other people's experiments in detail, how they write it. And this is an easy experiment to do. You get the radioisotope, have your friend do it if you want, and explain this away. You're not going to explain it away. This comes from the subquantum effect. And then if you're so inspired, then you can do the experiments that I set you up to do. They're, as experiments go, easy experiments. I did it in the living room.
All right. Another question from Dave. I like what I'm hearing. What do you see the application of your subquantum work, like computing, communication, nuclear fusion?
It
He's asking
Yeah,
about the
that's right.
application.
That's good. Look, I expect plenty of applications. It's like saying, what would you do with electricity when electricity was first figured out by Faraday? Plenty. So straight away, I give good example as to the application in spectroscopy, and I'm sure you're going to come up with other applications all across science. So it's about getting the basics right without wave particle duality to understand what is matter and energy. So it's an important step. Yeah, the application to start with is right here in spectroscopy.
Okay. Thanks.
Thank you for that.
Yeah. Thanks, Dave. All right. Do we have more questions, Eric?
Can I ask you about this loading? It looks quite interesting. It's good to challenge, the establishment. I didn't understand fully this loading model that you talk about. So I'm imagining that your loading model could explain possibly this entanglement. But then, what's the actual mechanism, physical mechanism of this loading that you're referring to, and where the energy would come from?
It comes from noise, ambient vibrations, previously absorbed gamma radiation. It's all there ahead of time. It and it's realized from understanding the signature of the experiment is not a whole H or a whole M. It's that the ratios are quantized. It's about how to look at the experiments that display wave properties and see that you don't need a particle to show up to make the click, that the wave can transmit its identity by the detail of the ratio that's conserved of things we know about, like charge, action, and mass. So it was a big clue that Planck did his action constant as thresholded. And I'm showing that it could be the same way to look at it with charge and mass as being thresholded. So when you put all that together to look at the constants, to have that property that we're quantizing the ratios and that the constants are thresholds, then try seeing how that could happen in these experiments, that it could load up. This is the key of the concept, the difficult concept. It took me years to fuddle around before I got it. The beats and the thresholds were pretty straightforward to come up with, but this is really the key, the principle of conserved ratios in what gets transmitted in the wave. So the energy ahead of time is what everything is made out of. We live in a sea of gamma rays. It's vibrating everything. So maybe you want to talk to me later about that, but thank you for the question.
Yeah, thank you too for your answer.
Okay, thank you. There's another question from YouTube, from Dennis. Is the electron as a particle have a mass quantity that is actually the mean of a probability distribution? I think that there was a similar question asked earlier.
It depends on what experiment you're looking at. It depends if you're looking at experiments that express this wave property, or if you're looking at some bulk matter experiment. The bulk matter experiments will be will have the electron mass and charge constants rally together by the nuclear wave functions. It's pretty much going to be expressing the threshold aspect of this theory. But it doesn't always have the threshold aspect, is my point. When you smear across space, it loses it. Because how would you diffract particles? They've been trying to diffract particles for 100 years. It doesn't work. I'm showing you do not need to do that. If it shows itself as waves, maybe it really is waves. Then it comes to the question, how do you explain the clicks or the particle-like properties in our experiments? So that's what I've addressed in many examples here, and by experiment to show that the probability interpretation fails.
Okay, good. Thank you. There is a question from Terry on the chat. Terry, maybe you could unmute yourself and ask.
You want me just to state the question, or?
Yeah, so there is a
Hear me?
question. Yes, we can hear you.
I was just wanting to run through, if you could, Eric, an example and scenario. You just have one gamma ray emitted from a low capacity emitter. It's in a spherical detector. You have detectors that are way out, meters away, whatever you want to choose.
What?
I cannot for the life of me say how a threshold model works in that. How do you load up one particular detector? Would you agree that you will get one detection from one detector or not?
That's what it's about. You can
Okay, but
see the
do you
clicks,
know-
and it's not meters away either.
Well, they could be meters away. I
They
mean,
could be, but it may not work meters away.
well, why not?
I-
I mean, you still get conservation.
I'll show you why not. I did an experiment for that. This experiment says why not. It's about taking advantage of a near field shock wave. So the distances matter.
Well, it's still conservation of energy, Eric. I mean, you have,
I know about energy conservation.
well, then why does it?
But you're
show up
thinking
the
in
laws of
terms of
field?
particles when you say energy conservation. The experiments pit you against energy conservation in general, or if you're going to unquantize it. I'm saying energy conservation does not require particles, does not require quanta. I'm showing how energy conservation works unquantized.
But again, I'm not asking you whether it's particles or not. I'm asking you, and I think you gave the answer, that if you have a single emitter at the center of a large vacuum chamber, you seem to be saying that if the detectors are close, you'll get a detection one thing, but you also seem to be saying that if the detectors are far away, they won't. And I can't agree with that. I've never.
All right. All right.
All
All right. All right. Look, it depends on whether we're talking about matter or light. For light,
Gamma rays. I wasn't switching.
gamma. All right. For the gamma rays, I did that experiment. It's right here on the slide to show that distance matters.
Are you claiming that gamma rays disappear over distance and do not hit the detectors?
Frequency is conserved. The intensity of the classical cone of light will go down,
Yes.
just like a classical ray.
No disagreement with that. For gamma rays, ordinary rays, what you might call
Right.
photon, I don't disagree with that.
Right. So in a near field where the cone of the gamma ray is close to the size of the absorbing molecule, the absorption by the photoelectric effect will be higher. And you'll be able to click off more than one detection from that classical cone of gamma ray energy. That's what it looks like from all these experiments, that what's going on, and that light does not hold itself together in a particle, as soon as you do that, you have quantum weirdness. You go to this other model and you can explain and show the 2-for-1 effect. So look, there's a whole lot here. I don't know how you'd explain it away. Go ahead.
Well, no, I'm asking you the question again. I guess you
Okay.
answered it.
Go ahead.
You're saying that a large detector, the gamma ray, actually, I got mixed up. Will it register twice, once? It varies. What were you saying?
It registers twice. There's 2 clicks in this experiment. Actually, there's 3. There's 3 clicks in these experiments. There's one in a trigger detector, and then there's in the larger detector behind. And the distances are close. This is like an inch away. It's a 3-inch diameter crystal. So we're seeing multiple flashes in the detection of detection from a one-at-a-time source. That's what it's all about. So that's what it's all about. Going back to this, to see, well, does the source emit one at a time? Yeah, we know that. This is a very well-respected test. And we see that there's a band of noise in the time difference histogram. Then we rearrange the detectors, and lo and behold, now we see 2 at a time, or even 3 if you look at it. That's what it's about. So it's about seeing, is light quantized? The answer is no. E equals h nu is still correct as an energy of detection, also as an energy of emission. So the model is that on emission, it's initially h nu energy, but thereafter it spreads classically. On absorption, there's a loading up, and then at a threshold, it'll give a click that is the h nu, and you could put all these together over time, and you will see energy conservation. So,
So your assertion is that, and this is part of your threshold idea. Your idea is that if you send out one gamma ray, fresh experiment, set it up, one gamma ray gets emitted. If it's far field, I think you're saying it would get no detections at all in the broad case if the detectors were very far away. Is that correct?
no, you'll still get detections. It just won't show up as often in coincidence.
Well, you see, right. Statistically, in the average, you're going to get your total. If I'm trying to recall your previous talk, you said something to the effect that like there's a temporal mismatch, that you get a total number of gamma rays that match, but the individual gamma rays don't necessarily correspond to speed of light detection of the detectors. Is that kind of right, what you're saying, or not?
Well, first, speed of light isn't a factor. The wires are too close to wonder about whether there's some half a nanosecond difference. So there's no speed of light correction necessary. One thing I want to say to try to clear this up is that when these pulse peak, when this band of detections goes up, these in the wings of the histogram that are out of time will go down. So when you add it all up, that's where you will see energy conservation. But the peak says there's a mechanism whereby there's something that allows it to go together in time. And that's the near field shock wave of the gamma ray that is emitted that could set off loadings to threshold in the pair of detectors.
Well, when you say near field shock wave, you're talking about it within material detectors as opposed to in empty space. Am I correct?
It doesn't matter. It doesn't matter whether it's in the detector or space. It's just that if you push all this further away, like in this test that I did, where I move the source back, then it goes into more of a far field.
And you're saying that the far field on average will conserve energy, but in short term, not necessarily, or at least not.
This business about conserving energy, it's very confusing. People talk about conserving energy in a particle sense. And I'm saying to transcend that, we can understand energy conservation without quantizing. There's a difference.
But I think you would agree. First of all, I don't have a problem with saying it's energy, you know, E equals mc squared, or the full Dirac equation with momentum. That's conserved, right? Or
I don't know anything about the Dirac equation.
well, that's just the extended version where you add momentum.
That,
E squared equals momentum squared plus. Well, at any rate,
I don't know about it.
but you're not disagreeing with conservation. You're not disagreeing with conservation of energy, right?
Of course. That's what's so great, important
I
here.
just want to make sure, because when we're
Embrace
talking,
energy conservation.
yeah, when we're talking about it this way, though, it comes over as if there could be a violation. I don't think that's your intent. That's why I'm trying to emphasize.
Right. We embrace energy conservation
Okay.
and show that we're violating quantization.
The reason the threshold models got dumped, which they did, they got dumped. They abandoned them early on, is just for the simple reason that one photon is a darn small amount of energy, and you need an enormous amount of loading before you're going to trigger a threshold at some distant location. So but that's why they abandoned it. It's because they couldn't see a way to do that. So can you comment on that, on how because I hear your description, but I don't understand how you're dealing with that.
Here's how I dealt with it. I dealt with it in the beginning of the lecture by talking about the element of time of loading up to make the photoelectric effect happen. People will have you calculate how long does it take to load up for that energy to emit an electron. This is what taught everybody away from the loading theory. So what I'm saying is wrong is they're starting from zero to load up. They're not understanding that there could be a preloaded state where all it needs is a small amount, the way Millikan guessed that it would be. They did not use that understanding when they compared to experiment, when they discounted the loading theory.
Yeah. The whole reason why I asked the spherical question was to try to get that issue of how do you get this thing loaded quickly enough to do that.
You don't need it to be loaded quickly enough.
Well, if you're loading,
it's preloaded all the way up to some semi-stable state. It just needs a minute addition, like Millikan guessed.
Right.
It doesn't have to have the whole amount loaded up. That's why it was rejected. They're calculating as if it was unloaded. How long would it take to do the whole thing? You get way too much time.
I understand it. You got some interesting experiments, but I don't understand what you're saying that gets around that. I'm genuinely not following what you say is the addition to the theory part that you said gets around that. So
it's just like having a preloaded state in the cups. It could be way up, and all it needs is a little bit more to add in. You get energy conservation by understanding there's something there ahead of time. It doesn't have to start from zero. There could be plenty that's about ready to be kicked off.
Now, if I interpret what you just said, it sounds like you just said that if you have a series of detectors outside of that, that the entire set of detectors is already preloaded at the gamma level and just waiting to trigger, and one of them eventually gets triggered. And
Not all of them.
not all,
There could, no, there's just some. It's
and how do you get that sum? That's where quantum theory gets weird for everybody. And I don't see how yours is weird any different, because if only one gets preloaded, how's that different from quantization? Seriously.
it's not just one. If you see 2 for 1, you could see 3 and 4, and I've seen that.
But still, you see what I'm saying is it doesn't matter. It is very interesting that your experiments see more than one. And by the way, I want to emphasize that. I think that's a very interesting feature of your experiments. But the scale is still amiss, because you still, if you say it's 3 or 4, you still have to say those 3 or 4 somehow got preloaded. Okay, so
They were preloaded.
They were preloaded.
Yes.
But where's the what's the mechanism for the preloading? And this is the same question I know I asked last time, but how does it get preloaded? I mean, and you can just say I don't know. That's fine, but I'm saying if you're going to go that path, I'm trying to understand why should all the gamma ray loading go to only 3 atoms?
It doesn't all go. Just
Well,
sometimes. It's just about comparing to chance.
But sometimes that sometimes is so critical. Smooth radiation emission, which I do agree. I think photons get, our light from distant galaxies get focused by lenses the size of, 10 million light years apart. I have no problem with that. I think that's a real issue that you can't ignore that.
Right.
But I still not seeing how it winds up where's your sum coming from? Where's your sum of this? Where's your allocation coming from? Does that make sense? How's this stuff getting picked? Something's getting picked. Something's random. Where's that randomization coming from?
We do not know
it's not an
this preloaded state.
There's 3 or 4.
The randomness is the unknown nature of this preloaded state. There is still a randomness.
I'm fine with that. As long as you say it that way, it's the unknown nature of your preloaded state, I'm fine with that. And also, I acknowledge that because you're getting if I understand your experiments, you're getting results and levels of interaction that you shouldn't be getting. I understand that. That's the interesting part of your experiment.
I'm sorry you dropped out.
What's that?
There was a dropout in hearing you.
Oh, okay.
All right. Thank you for saying it's interesting.
No, it's interesting, and the fact that you said that the preloading is mysterious, I'm actually fine with that. If you want to try to go that approach, as opposed to just you would agree there's something mysterious there.
Well, there's surely going to be more information to dig up about it, but I'm forcing the issue by comparing to quantization. I'm pitting quantization against energy conservation. I'm saying you always have energy conservation. Are you going to still hold on to quantization? The experiments say no. Therefore, there has to be something there ahead of time. The mechanism of loading up, there's going to be plenty to learn about it later. But first, one step at a time. It's loading up.
Now, again, clarification, maybe for somebody else listening. You're not disputing that photoelectric effect exists, are you?
Of course not.
Okay,
the equation is right, but I'm redefining the terms in the equation, like saying Planck's constant is a maximum and the mass constant is a maximum. The message of the experiment holds.
Okay. Now, I'm going to switch gears completely, go to another one, though, because you've said this a couple times, and I'll try it anyway. I don't want to get into an argument about this. You keep saying that particle diffraction doesn't happen, and I don't know why you say that. Electrons
because it's not particles when it diffracts. It's a misnomer to just say, well, sure, you could say, oh, it's a quantum mechanical particle that has this property of a probability wave. No, I'm saying it's not particles. There's a confusion between saying quantum mechanical particle and classical particle.
But you're saying that the electron is a wave.
When you see diffraction, it's a wave. There's not particles being guided. That's what the experiments of the alpha diffraction thing say. That's
Eric,
what's going on.
you might be shocked to find out that I agree with you completely on that.
All right, thank you.
Because
That's
I
great.
I have problems with Hilbert space. The dynamics are wrong. You cannot, there's infinite darkness in Hilbert space. They always wind up actually shortcutting it and putting little lightning bolt shoots through it when you start talking about dynamics. It's a great way to describe the potential states, but it's a terrible way to describe dynamics. I am agreeable with everything being a wave, but there's this weird thing going on where the wave gets shrunk down, or I don't know. Do you use what do you call it when the wave winds up at one spot? Do you have what's your term? So
No, that's not what I'm saying.
I'm just asking you.
Not,
what
that's a wave collapse of the wave function thing. I'm saying it's not collapse of the
how do you
wave function.
describe you got a wave going there, you got the loading. I'm trying to understand, but at some point when it locks onto a particular detector, you would agree that I think you would agree. Well, let me just ask you. You would agree that you don't see that energy anywhere else at that point, or do you? I don't know. You have energy conservation.
Sorry.
So
yeah, there's energy conservation. Of course there is.
all right.
Not all the wave will get sucked up. There's no collapse of the wave function. The wave function collapse is about non-locality. We're getting around that. I'm saying that we're getting around this non-locality. It's not collapse of the wave function. I'm saying it's more of an inside-out threshold effect. I'm saying the inside-out discontinuity.
Eric, I think we lost you again.
Loading up from the inside that reaches the threshold inside.
Again, you might find it interesting that like I've written a little online short paper about the non-locality not being a physically describable concept. Because every time you look at non-locality, there's no version of non-locality that works without first traveling at the speed of light to get to the destination, and that's Asher Perez was the one who first really pointedly
that's a good first step. We reject. Good.
Yeah, but no, I because I no longer can state non-local. When you do something, it does not affect anything other faster than the speed of light, and that preempts non-locality in the sense of how we usually think of it. But it requires some pretty weird.
It's not so weird anymore.
It's when the first time I ever read that from Paris, I remember saying I agreed exactly with what he was saying. I had no idea what it meant.
Who?
Asher Paris. Asher, really, really good physicist. You might want to look him up. He had a 2004 paper where he talked about how you do not that when you have Alex and you have Beth. Alex makes a measurement. His point was very simple. Nothing changes at.
I'm sorry, your audio broke up.
Whatsoever. Oh, can you hear me?
No.
At any rate, Asher Perez, he just pointed out that the speed of light is a firmer limit than people give it credit for. You don't change a distant galaxy because you tickled on an entangled pair. You did,
right.
Yeah.
Of course.
So, but yeah, if you don't accept non-locality as a physically testable phenomenon without first approaching the object in question at the speed of light, thereby fully obeying the speed of light limits, you have a very strange situation. But it's not the same thing as non-locality. It's not the same thing as instantaneous action at a distance. And I think that's a fascinating area.
The 2-for-1 effect and seeing that there's a sub-quantum state does not seem so strange to me.
Well, space, every definition of space, and this goes back to Einstein's 1911 paper, in order to make space a physically testable concept, he had to go through an entire algorithm for how to set your clock, put your clock, move the clock out there, put a bunch of clocks out there, create a cloud of clocks. And then he concludes by saying, and now you can make physically meaningful experiments. And if you stop thinking about that, that's an amazing statement, because he's saying that the actual concept of measurable space is dependent on setting clocks out there first, which of course it is. If you don't have any clocks, you can't measure anything. So space is a much more information concept than it is just a simple variable. You know, there's a lot to it.
Look, I don't know why you're bringing that up at all. I'm not dealing with relativity in any way. I'm just dealing with classical waves and seeing if the probability interpretation holds up.
Yeah, please understand, I meant that actually as a supportive concept, because I'm saying there's some of these issues about how that works would seem to be related to why you're getting results that don't match the usual. Leave it at that. But that was
It
not
doesn't match because the other experiments did not know what they were dealing with to try to show the distinction from. They didn't have any idea of what they were trying to disprove, like whether there was a preloaded state or not, and whether they should have energy resolution in their detectors. Nobody did that. Nobody looked at the beam split coincidence experiment in a reasonable way to show a 2-for-1 effect where they had energy resolution at all. It's a strange place I'm coming from to say this very fundamental thing. What happened to energy resolution in the detector clicks? They throw it away. It's all photons to them. It was a mistake. Use energy resolution in the clicks of the detectors and see the 2-for-1 effect. Compare it to particles, and particles go loading up. There was a wave that went there. It filled the loading. It's very simple to me. And then you look at the symmetry amongst the equations that display wave properties, and it starts to come clear. That's what I'm saying to do. Look over what I wrote in these lecture slides. The lecture slides are about reading over the loading theory, why it was rejected. There's more of that in my previous lecture, where I showed the element of time in the photoelectric effect. There's a bit more of that in the history lecture. So look, I appreciate.
One of your key points, Eric, is the throwing away of the resolution
You're talking with me.
energy detectors, right?
Energy resolution in the detector. That's right.
That is one of your critical points, is saying if you include the resolution, energy resolution, you start getting a very different looking set of results than you do if you just discard that, correct?
You had a dropout. If you include the energy resolution in the detector, you add up coincidence that are, if it was a particle, it would break that model. It's a 2-for-1 effect. You're starting with 1 H nu emitted, you get 2. How do you do that? That's what it's about. It's
okay. That's what I was asking you. That's what I was verifying. That's the key thing that you're trying to get over about what you're
particle energy resolution. This idea of linking particles to energy conservation, that's the mistake. It happened way back when they analyzed the Compton effect that way. And I gave some references as to how they think and write about that. It was from the particle interpretation of both the photoelectric effect.
I have a question.
They were thinking in terms of what I call particle energy conservation. That's to be
I have a question.
Yes, please. Mm-hmm.
Yes. How did you come up with the idea of calling your research on quantum physics. Are you the first one to work on this project, or other people work on this project before you? Thank you.
It's all mine. I came up with the idea. The whole business is mine. I had a little help from my friends, but it's a very small contribution. It was my idea, and to say unquantum.
Yeah. Well, so how do you
There's
get there?
something
Why
there
do you call
that's
it?
not quantized. It's just a little trick with words to say unquantum. If everything was formally quantized, there would not be such a thing as a sub-quantum effect. So I'm kind of being nice by saying it's a sub-quantum effect, but really it's not quantized at all if you have a sub-quantum effect. The idea of quantization is like integers that denies anything fraction. I'm saying there are fractions. It's just hard to see. You have to know what you're looking for. And you have to have some idea of what the model would be ahead of time. So it's hard to take, but everybody says quantum, 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 everything. And here's this guy saying unquantum. I get it. Yeah, it's thresholded. There's a sub-quantum effect. Go ahead.
Wow, amazing. Thank you. I'm very impressed.
You're impressed? Thank you.
Okay, good. We have a few other questions. Eric, are you still available for us? Do you still have time?
And one more question. So, how can we apply your theories? How will your theory be useful with today's research, like AI, quantum computing, security, and energy?
Someone needs to reproduce the experiment. Just to start with what I've done. Like I say, start with just a single detector spectrum and see the anomaly I pointed out. Do the two detector experiment. See how it relates to material science with the spectroscopy, where I showed evidence of. Just needs to have somebody reproduce the effect so that we're not all completely ignored forevermore. People always ask me, who reproduced the effect? Well, there is one friend of mine across the world, but I haven't heard from him in a long time. So I'm encouraging anyone to give it a try, and I'll help you. I'll come on with you every week for an hour at a time and on video and help anyone reproduce the effect.
So, have you tried to collaborate with other schools or university to work on this project, or test the result of your research?
I would love to find some way to collaborate with me. I'm routinely someone collaborate with me. Please collaborate with me.
Oh,
All right. Okay, it seems that there are some connection issues, but we'll try to ask one more question. Okay, there's a question from YouTube, from Dennis. I have an electromagnetic model of the electron that has a standing wave nature. Is this consistent with your theory?
I don't know what's wrong. I can pick up what's going on here. An electromagnetic what?
Sorry, let me go back. Electromagnetic model of the electron that has a standing wave nature. Is this consistent with your theory? I've
seen many people try to do that. That they try to say that it's an internal photon running around as being the nature of charge. That might be consistent with a bunch of equations. I personally do not think it works that way. I think the matter wave and electromagnetic are different things. But have at it. I just don't think it'll work that way, that electromagnetism would hold itself together. Electromagnetism is the furthest thing from what would it take to hold itself together like that. You'd have to have some particle nuclear field that is so strong to have it diffract in a circle. Look, I don't know. I just don't think it works that way.
Mm-hmm. All right. Good. Do we have more questions? Maybe let's
I have
change.
some difficulties
Yes, please.
about spin, particle spin, and the particles. This is what they call entanglement, which is synchronizations of 2 or 3 particles spin. So how your theory regard the preloading loading is
All right.
relates to these spins, particle spins?
All right. Well, first of all, has anyone done that experiment? No. No one's done the experiment. They talk about it as if it's been done, but it has not been done. Look at the experiments, please. It's a thought experiment to say that the spin is related like that. What's been done is with electromagnetics and not coincidences with any kind of rest mass. As far as I know, I don't think it's been done. So if you'd like to tell me a reference of somebody who did that, that's nice. I'd like to read the paper.
Eric, what was the spin experiment they just referred to?
It's a thought experiment
Which one?
where people think that some spin from that has a signature on one side will affect what happens on the other side by entanglement. That was from David Bohm's theory,
Okay.
right?
You're talking about classic spin entanglement.
Right. That's the theory. I don't think the experiment has been done at all. It's not been done.
Well, I can go on the internet right now and buy.
Oh, go ahead. Look, tell me. I've never seen it done. People just talk about it as that it should work that way. But please, let's stick to reality here.
Are you familiar with the encryption equipment I'm talking about? Because there is equipment you can buy on the internet based on spin entanglement.
There is.
Yeah.
It's light.
Well, I'm sorry, what?
It's not matter waves. It's
No,
light.
it's well, yes, it's light based. Yes,
Yeah, so they're
it's called
applying spin to light.
electron case. The electron case.
I don't know of anyone doing that.
You're talking. No one has done the electron case. Is that what you're saying?
That's what I'm saying.
Okay, all right. That's an important clarification. I thought because the photon case, and again, even when I use the word entanglement, I actually have a mental qualifier because again, I don't believe in non-locality. Speed of light is everything. Everything.
Good. Right. We're buddies.
On that point, yes, we no disagreement. And also, I think the arguments are surprisingly simple. And Asher Perez, again, was a well-known physicist and just said that more pointedly than anyone I'd ever seen before. So, yes.
So basically, you are rejecting so all this quantum biology, like photosynthesis and et cetera, which are based on the quantum physics, quantum mechanics, which are related to the superposition and entanglement. So you say that this is not real.
Right. I'm saying entanglement is not real. It's something that they pull out to try to explain phenomenon, but there's something else going on. Let's get one step at a time to see if entanglement is real in experiments that are done without a whole list of assumptions behind it. like I showed you in other people's experiments who tried to do this. I don't think they did the experiment right for just this, what I'll call the single particle experiment. And single particle entanglement experiment is the beam split coincidence experiment that other people do and I do, and I showed the history of that. But they interpret the two particle experiment by the single particle experiment. They think it's all a done deal with the probability wave from the one particle experiment, the beam split coincidence experiment. They think that is done right. So then when they go to the two particle experiment, they interpret it that way with quantum mechanics, with the entanglement. And they may see coincidences there, but it's not for what they think. And also, there's a hidden variable that's not accounted for in Bell's theorem, which is the preloaded state of my discovery. So I'm imploring people to look back at these details where they're just going over them too fast. They're skipping over the basics. We don't want to embrace entanglement and non-locality. It's too weird. The world would have to be made out of ghosts. And there's this whole list of acts of desperation that I'm sure you're aware of, that I listed here, like many worlds. This is the problem. And it comes from energy quantization, from the one test, from this test. It comes from this sentence to understand that this is about something that you cannot visualize. They understood it that far back, but it's never been thrown away. They think it all works that way. They never did the experiment right. Here's how to recognize what the experiment should do and what they did and how to do it. It's easy to do. I very much appreciate the opportunity to talk. I encourage anyone to look at the end of this lecture slides where you'll see my email. I think we should go now.
Eric, can I make one last comment?
Yes.
On the question about Catano.
I have a question. I'm sorry that you.
Okay.
Yeah, I'm sorry. It's a very interesting. You're talking about very interesting stuff. So you say that what they call entanglement is not entanglement. So how do you call it? And so how do you define entanglement?
It's just straight away from where I started in this the lecture slides, is entanglement. This is one particle entanglement. If it clicks in one detector to the extent where it eliminates the other detector, that's a one particle entanglement. That's the first simplest kind of entanglement. And that was recognized in these early people who wrote. No, I'm not here. It was recognized by Heisenberg about immediately becomes zero, the faster than the speed of light thing here. It was recognized way early that it's this first part of the beam split coincidence experiment and this idea that would go in one and only one. That's actually on an average, but still, that's on the average is enough, that it eliminates that it can go both ways. Because to go both ways and starting with what you think is a photon and then make two, that would be unquantum. But they say it goes one where it holds itself together, but it's entanglement is about both parts of the photon. To understand that this wave effect must be something that goes both ways, that is in contradiction to the one way or the other first part. So if you want to understand quantum mechanics, it starts right here with this sentence and what entanglement is. and it's never changed.
Eric,
There was another question. I'm listening.
if someone had a question, I'll pass. Somebody else?
No, Terry, it's your turn.
Just in response partly to Cateno, I'm sorry if I'm mispronouncing your name. I almost certainly am.
It is fine. It's okay. Thanks.
In the case of photosynthesis, I don't think you really, especially because of the small spaces involved, the idea of entanglement over a long distance really doesn't, I don't think it's a necessary part even of the mathematical formulation. It's a fascinating phenomenon in terms of the probabilities, though, because you are certainly bending the probabilities in very interesting ways to get the excitons to where they need to go. And that's similar to the same stuff that the Nobel Prize was awarded to Hopfield. A couple of his papers in that same topic were mentioned. There is something very fascinating going on with those probabilities at that level. At least some of it has a lens-like explanation. I've seen overly exotic explanations of the energy transfer, where if you simply look at the bundle as essentially a phase coherent transfer mechanism with a lens-like property, you actually come up with a pretty good model of it. And that's a far less exotic way of explaining it. But even with techniques like that, there's just a deeply intriguing area. And my objections to entanglement, again, are just, they're never complete models, never. They always talk about the entanglement as if it's already happened. And reality does not work that way. You do not get an entanglement measurement ever until you have followed the speed of light. And again, this was Asher Paris's observation, not mine. I was as baffled by it the first time I saw it. And I've since converted over to completely. I said, no, he's right. It does not exist until traditional speed of light velocity limitations are met. The entanglement I talked about, that you have to spread the photon first at speed of light before you get these interesting probability relationships. So you still, the probabilities are what is weird. Not the speed.
Look, it's good. There's no entanglement. The reason why I don't really see the issue you're bringing up, but the reason why entanglement is lived so long is that they think this effect that I'm pointing out in the beam split has been done correct. No one's come up with a way to show that this experiment gets the opposite answer. Well, it's straightforward to do. And then there's no entanglement. It seems straightforward to me. And for photosynthesis, well, look, there could just be a loading that shows up, and it doesn't have to make a photon do a crash landing either. Look, photosynthesis is sensational. I'm working on the secrets of life with another experiment as well. We could talk about that sometime. I'm listening.
Yeah, thank you both. Thank you to Eric and Terry as well for your comments.
Okay, good. Thanks.
Eric said I should repeat your work.
I think I heard a thank you. Well, thank you too, my friend. Very good.
All right. Good.
Okay, thank you.
Do we have more questions? Helen, I see that you sent me a question, but it has been already asked. No, there's another question from George. So George cannot unmute. Perhaps nearby, the detector is at a resonance peak and farther away at the inference true. However, these detector distances are at a vastly greater scale than the wavelength of a gamma ray. So maybe I will just also post this question here to everyone. Yeah, I'm not sure actually if it's a question, but yeah, maybe rather it's a comment, but yeah.
The wavelength of the gamma ray,
yes,
will be related to the transverse spread, as I've seen in I'm trying to find the experiment where I found a distance effect here. The wavelength of the gamma ray will affect the angle of this cone. So it's just about the efficiency of whether we're going to have enough classical energy in the cone to trip off detections more than one from one cone of classical light. So when it gets spread out too thin, there's less energy. The frequency is conserved, and the absorption has some sense of resonance to it. It's not any frequency that gets absorbed. One of the objections that I've heard is how do you get exact frequencies to match up from the source and the detector? There are plenty of frequencies to go around. And I like bringing up this analogy. It's like singing into a piano. Sing in a note in between the two notes on the piano. It will echo back what you sing to it. It finds enough frequencies. That's kind of crude, but I don't use this frequency match thing as a way to throw away the model. I'm not sure if I addressed the issue you said. There was something about distance. So say something.
Okay. Yeah, so George has just said thank you. So I believe that this is a good answer and that it answers your question, his question. All right. Do we have more questions? I don't see more questions on our chat. Maybe someone would like to unmute, and this is the last chance to ask. Okay, I don't see more questions, so I think we can officially close. So Eric, thank you once again first for the great presentation and for answering all the questions. That was a very interesting and fruitful discussion. I believe that we all enjoyed. So
Great.
thanks.
I very much appreciate. I'll do this again anytime. Thank you.
Great, thank you. And we also thank all of you for attending and also asking the questions, participating actively in this discussion. So thanks for that, and we hope to see you next time.
Bye-bye. Thank you.
Thanks. Bye-bye.
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 Oh, gosh.
Oh, man. I'm tired, dude.
Oh, here's stuff.
Yeah, I'm tired.
Uh-oh. Uh-oh. I think I heard Dave.
Yeah.
Uh-oh, you're still here. We're still here.
The living room. Look at this living room.
How are we all still here if we're all gone?
It's one of those quantum phenomena. I'm going to go now. I have to go. Believe it or not, I have to go to the John Deere dealer and get some parts. Bye.
Thanks for being my friend, Dave. Bye-bye.
Bye.
Gosh.
All right, good luck.
I'll need it. Thank you. Bye-bye.